Having understood the types of blood vessels, the characteristics of blood vessels, now we are ready to understand the main purpose of blood vessels, which is to deliver blood from the heart to the tissues and again collect blood from the tissues and return it back to the heart. And from there to the lungs for oxygenation, or from the heart to the kidneys for removing wastes, etc. So all of that can be summarized in one word that we need to focus on, that is flow. Flow of blood through the blood vessels is the main focus of this video. Okay, hemodynamics is the blood that flows through the vessels and what factors affect blood flow is one thing that we would do. So when we are talking about the blood flow, we can divide that into blood flow within the arteries, blood flow within the capillaries, and blood flow in the veins. They are very distinct. And I'm afraid this is going to be a long video from that point of view. Well, let's begin. So first we talk about the types of blood flow. If you're thinking about a nice large artery, blood would flow mainly in the laminar fashion. That is very smooth, quiet type of flow. Whereas the blood that's close to the blood vessel wall may have some restriction. The nature of the blood vessel, maybe a curve here, maybe a twist here, maybe a thickness in there, etc. So that delays the flow of blood. So it's not as smooth as right in the center. And you can see that the one in the center moves faster than the blood that is close to the blood vessel wall. Still, it is nice and smooth. Now, what you're seeing here is turbulent flow. So if there is resistance right here, blood is not getting through the space as easily. That could be the cause of turbulence. Or the force with which blood is allowed to move through the vessel. Okay? Faster than the blood vessel can handle. That could be another cause for turbulence. You may want to test this with your tap. You may release the tap gently, so there is this nice flow of water, very quiet, and then increase the speed with which water flows, then you see this gushing sound. That would be turbulence. All right, so we have two distinct types of blood flow. I have given some other details here. Laminar flow is a parallel flow, occurs when velocity is low, that is the speed is low, and the fluid is viscous. Outermost layer is stagnant, whereas the layer at the axis of the vessel has the highest velocity. That's what we saw here. Close to the vessel wall is rather slow compared to the main axis. All right, so velocity is the speed with which blood flows. Turbulent type of flow is where there is increased resistance to flow, there is that whirlpool action, or high velocity with which blood has to flow. All right, either one could cause turbulence. So more details are shown here. Laminar flow occurs up to a certain velocity, up to a certain speed, after which its pattern breaks down, particles move in irregular and variable paths, and that's what we call as turbulence. All right, the critical point at which this kind of transition occurs from a laminar to turbulent flow is defined as Reynolds number. Okay, Reynolds number is the one that helps us figure out what the ideal velocity is to make the blood flow smoothly in the laminar fashion, and what speed, what velocity would switch it to Reynolds to turbulent flow. All right, so let's take a look here. Laminar to turbulent flow measured using Reynolds number. So we have this critical velocity that we are trying to figure out is where you're talking about Reynolds number. This is eta, that is viscosity of the blood. And then 2 is a constant here. And you're talking about density as one factor and the radius of the vessel as another factor. Okay, so that is how you would be able to determine the point between laminar flow and turbulent flow. All right, now we are going to talk about blood flow and the factors such as pressure and resistance and their relationships related to blood flow. Okay, so let's recall Ohm's law. Ohm's law is mainly to explain electricity, the flow of electrical charges, voltage, and resistance. But here we are talking about Ohm's law in relation to blood flow with some modifications. Here, Q is the blood flow. All right, Q equals P1 times P2. This is P1 times P2 is actually the pressure in one part of the vessel and pressure in another part of the vessel. So the difference in pressure between one part and another part. So usually, as you know, blood flows from higher pressure to lower pressure. So you're assuming that blood is going from higher to lower pressure. So this would be a higher pressure and this would be a lower pressure. So these two numbers together would be called delta P. Okay, delta P. And blood flow is directly proportional to pressure, difference in pressure, whereas it's inversely proportional to resistance. Think about it like this. Higher the pressure with which blood is pushed, greater the flow. Resistance is the opposing force. If there is opposing force, the speed with which blood flows is limited. Okay, so it's a fine balance between the pressure there is in the blood vessel and resistance there is that's opposing this pressure or this flow. All right, so that is the relationship we're talking about. Now, determining resistance, how much resistance is there in a blood vessel is explained as Pucell's equation. Okay, a French scientist, Pucelle, it relates the velocity, the radius, pressure, resistance, viscosity, all of that. All right, the length of the vessel and so on. Okay, so let's talk about blood flow that is in milliliter per second. Here you have pi, delta P, that's the difference in pressure in the vessel, the radius to the power of 4, and 8 is a constant number, eta and lambda. So that is where you want to talk about which one is which. Radius is probably the most critical of the factors, all right? So you are looking at factors that are directly proportional, the factors that are inversely proportional. Eta refers to viscosity, okay? And then lambda is for the length of the vessel. All right, so longer the vessel, greater the resistance. Thicker the blood, or greater the viscosity of blood, greater the resistance. These are some factors that generate resistance. Okay? Thicker blood, longer vessel are the ones that generate resistance, whereas pressure is directly proportional. These are inversely proportional. All right, so using this formula, we can determine blood flow by moving the equation around. So blood flow is delta P over resistance. This formula we already came across before. And similarly, we can move this in a different way. You're talking about resistance is delta P over blood flow. All right, so there are mechanisms by which we can actually measure resistance. To increase blood flow, what do we have to do? Either increase the pressure or reduce the resistance, right? All right, so we have Pucella's law turned around to figure out resistance. This is where you would move 8 eta lambda here, and this is basically reversed, all right, over pi r to the power of 4. All right, with this, let's move on to talk about blood pressure in a little bit more detail. Blood pressure could be in the artery, referred to as arterial blood pressure, in the capillary blood pressure, and then the venular blood pressure. Okay, so what is arterial blood pressure? Let's talk about that. So this is the pressure that is measured as a force that's exerted by the blood against the blood vessel wall. All right, so that is where, when the heart pumps blood, it's released with a lot of force that hits the wall, blood vessel wall, and generates a certain force. That contributes to arterial blood pressure. All right, it depends on a couple of factors. These are the two critical components that we need to relate to arterial blood pressure. Cardiac output is one, that is the amount of blood released by the heart in 1 minute. And then TPR stands for total peripheral resistance. So how much blood is released generates so much force, correct? So this force is what we call as pressure. This pressure now has to overcome the opposing force. The opposing force is resistance. The opposing force is total peripheral resistance. So the pressure should exceed resistance in order for blood to move. Got it? So you already know that cardiac output depends on two factors mainly. Those are stroke volume and heart rate. All right, each one can be regulated and is regulated in many ways. Stroke volume is the amount of blood ejected by the heart in one heartbeat, and then heart rate is the number of beats per minute. Here is one example. If there is sympathetic activation, so I have shown the arrow as going up, increased sympathetic activation is how we read this, would cause increased vasoconstriction. If you recall, arterioles are the ones that are referred to as resistance vessels. They are the ones that are innervated extensively by sympathetic system, narrow lumen. So this is where you would constrict the vessels, and that results in vasoconstriction. That increases the total peripheral resistance. When you have increased total peripheral resistance, blood would have to be pushed through the vessel, and that is how you would increase venous return, increased cardiac output, and increased arterial pressure. So increased vasoconstriction helps move blood through the vessels and helps return blood back to the heart better. Okay, so you may be wondering how this is possible, especially if you are squeezing the vessels. How can the blood move? Well, veins are also supplied by the sympathetic innervation. Okay, veins are the ones that tend to pull blood, and this constriction here, vasoconstriction, this is global constriction. We're talking about not only the arteries but also other vessels. So the constriction of the veins would result in the pushing of blood back to the heart better than otherwise. All right, so that is one example of the relationship between the blood pressure and blood flow, and how that improves blood flow back to the heart. So we are coming back to the arterial blood pressure. This is where we have discussed the function of the heart, how the ventricles have to contract, and then the blood is ejected into the aorta, and there is this sudden increase in blood pressure within the aorta. This is the beginning of the aorta, where the pressure stretches the wall of the aorta. All right, and then there is that wave, we call this as pressure pulse, that is created, and that takes blood further along. All right, so this is measured, and it approximately takes 250 milliseconds to reach the peripheral arteriole after the ventricular contraction. Okay, so blood movement is slower and takes seconds. It doesn't rush through the vessel immediately, but it takes some time. Remember, there is resistance for blood to flow, and that is how it takes some time to reach a certain part of the body. All right, so we're talking about peripheral arteriole receiving blood from the aorta, okay, would take about 250 milliseconds. And you don't have to remember these numbers because the vessels are not given specific location, organ, or any of that, okay? This is an important slide where we learn the pressure in a couple of ways. You're talking about systolic pressure, diastolic pressure, pulse pressure, and mean arterial pressure. Okay, what is what? Well, let's talk about the blood vessel types in the x-axis here. All of the blood vessels are shown in the order they appear. Aorta first, arterioles, capillaries, venules, and the vena cava. All right, here you're talking about the blood pressure in a millimeter mercury. All right, so now what we see is this red line. Red line up here represents systolic pressure. Down here represents diastolic pressure. So you see this swing of pressure going up and down, up and down, up and down. What is this telling us? This is all within the artery. As the heart pushes blood, the higher pressure is systolic pressure. As the blood moves farther away, the pressure drops, and that would be the diastolic pressure. Right? This can be measured for quite a bit for distance within the artery, all the way up to close to the arterioles or up to the arterioles. Okay, you can see these waves of systolic and diastolic pressure. As you can see, it diminishes as blood moves further away. You won't be able to detect these swings as clearly as you would in the very first part of the arterial system. Okay, so you can detect blood pressure, systolic and diastolic blood pressure by placing this sphygmomanometer in an artery, fine, because you can still see them or hear them. But later on, it's not possible, okay, because the pressure drops and the waves also disappear. And then how do we measure pressure in these vessels? All right, so that is one thing we need to talk about. The second thing we want to talk about is what is pulse pressure. Okay, pulse pressure is the difference between systolic pressure and diastolic pressure. You see that here, systolic pressure could be 120, diastolic pressure could be 80. So approximately 40 millimeter mercury is what you call as pulse pressure. Okay. So the fluctuation that you see in pressure, systolic and diastolic, is pulse pressure. Now, the last one we want to understand is the mean arterial pressure. All right, mean arterial pressure is more or less a constant value compared to systolic and diastolic fluctuations. You see how you move from 120 to 80. You don't see that in mean arterial pressure. If you think about how stable it is, all the way up to the arteries, the pressure is about 93, 90, somewhere there, right? So that is a constant or a pretty much stable type of number. Mean arterial pressure can be calculated by using diastolic pressure and 1/3 of pulse pressure. All right, so that is the formula. Please remember this. Mean arterial pressure uses diastolic pressure, this one here, and about 1/3 of the pulse pressure. So that is the mean arterial pressure. So this number doesn't fluctuate as much as the other two numbers we talked about, systolic and diastolic. And as you can see, it's pretty stable here in the artery, but there is a sudden drop from the artery to the arteriole, and then that's pretty steep actually. So you're talking about anywhere from 93 suddenly to about 35 or so. So this is up to here. The red color is arterial. What you see in purple here is capillaries. Capillary pressure, you may want to kind of eyeball here to see somewhere around 35, and then the pressure drops as the blood continues to move through the capillaries to about 18. Okay, 35 to 18 is the mean arterial pressure within the capillaries. Then you're talking about pressure within the veins. The blue color is for the veins here, and the pressure that you see is higher very close to the capillaries, and the pressure continues to drop, and the pressure in the vein can be as low as 0, very close to the heart. Vena cava joining the heart may have a pressure of almost 0 millimeter mercury. So this is all about different types of pressures. Which kind of pressure do you want to measure? Where is all nicely illustrated. Okay, how do we measure blood pressure? Okay, you probably are already very familiar with this. I'm going to go through this very quickly. Auscultation is basically measurement of blood pressure. All right, here you have a sphygmomanometer. This is a very traditional approach, and you have the cuff that goes around the arm, and then you apply pressure using this rubber bulb, and then that inflates this cuff and constricts the artery that would be moving down the arm, and then that blood vessel you're actually constricting is the antecubital artery. All right, so when you're listening to the sounds using a stethoscope, you probably won't hear anything when the pressure that you have applied is higher and has constricted this artery. However, as you let some of this pressure leave, that's when the blood rushes through the narrowest opening that's created. That pressure is systolic pressure. As soon as you start hearing the sound, that's called first sound of Korokov, and that is systolic pressure. And you would you would hear the pressure sound continuously, the flow of blood continuously. And when the sound blends with the background sound, that's when the sound disappears. The point where the sound disappears is diastolic pressure, the second sound of Korokov. All right, so that's how you measure. I just wanted to go over it. And here is a nice illustration of what goes on. Systolic and diastolic pressure is what is shown here. Now, you are also looking at the sounds, okay? The Korokov sounds in a stethoscope would be the gushing sound each time there is blood rushing through the vessel. All right, so that is what you're talking about. So here is where you're releasing the pressure. Cuff pressure is released, and that is where the sound begins to disappear. Last sound heard is when the sound matches that of diastolic pressure. So that is where you see these are the sounds. The very first sound you hear is when the blood gushes through, and then you continue to hear the sound. Here it disappears. Got it? And that pressure where it disappears would be the diastolic pressure. Okay, so now let's move on to talk about some numbers. The systolic pressure is typically 110 to 120 millimeter mercury, and then the diastolic pressure anywhere from 70 to 80 millimeter mercury. All right, and now the ranges can be as wide as 100 to 150 systolic, 60 to 90 millimeter mercury diastolic, depending upon the age. Okay, the blood pressure is lower in infants and children, and it gets higher as a person ages. Older population would have a higher pressure than the younger population. All right, women tend to have a 5 to 10 millimeter mercury lower than men until about the age of menopause. So we already talked about mean arterial pressure, so we can basically skip this. Now we are bringing the blood flow topic in relation to the radius of the vessel, blood pressure, and then also the cross-sectional area. So a number of details that affect blood flow is what we are looking at here. The first one is the blood vessel diameter. Okay, larger arteries, as they branch, they become smaller and smaller. The smallest are capillaries. As they fuse to become venules, the size of the vessel increases. And as they fuse again and again and again, the size of the veins increase. And here you have the largest vessels shown. So arteries and veins, as you expect, are larger. Veins tend to be even larger than the largest arteries. That's one interesting point to make a note of. But capillaries are the smallest. These are the microscopic vessels. Good. This slide we have already seen. This is mean arterial pressure. We went over just now. What you're looking at here is cross-sectional area. Cross-sectional area is where there is extensive branching of the vessel. So you're talking about arteries having fewer branches. You're talking about hundreds of branches. Then you're talking about arteries. Well, we already talked about the branching of arterioles probably about 500,000 branches. So there it is, the arterioles. Then you're talking about capillaries. Capillaries have the greatest cross-sectional area. And, they branch enormously, extensively. So that is what is shown here. Okay, cross-sectional area, about 5,000 square centimeters. And then the cross-sectional area drops again when you think about the venules in the veins. Veins, again, you may be talking about hundreds of branches and hundreds of thousands of branches for venules and so on. Good. Keeping that in mind, now we need to talk about one more detail, that is blood flow. Blood flow through different types of blood vessels. Now, x-axis shows the different types of blood vessels. Now, blood flow is the greatest in the artery, and please note it drops in the arterioles. Arterioles have narrow lumen, okay, and they have muscular wall, so that limits the flow of blood, and that's where greatest resistance is among the blood vessels. So that is where the blood flow slows. And now take a look at capillaries. Blood moves the slowest in the capillaries. One other way we can relate this is greater the cross-sectional area, slower the velocity of blood flow is, correct? And then you're looking at venules and veins. See, veins have less pressure, and therefore you're talking about slower blood flow. So just to summarize, the pressure, the speed with which blood flows is faster in the arteries because of the higher pressure, and then moves slowly through the capillaries and begins to move a little faster than in the capillaries, but not as fast as in the arteries. Okay, with this, let's talk about some organs in the body and the amount of blood they receive and the amount of blood they receive during mild exercise and maximal exercise, and how blood flow is maintained steadily in a certain parts, whereas in other parts it fluctuates depending upon the situation. Skeletal muscle is one of the main bulk of the body, and then in a typical resting situation, you're talking about 1.2 liters per minute versus during mild exercise, it triples, even 4 times more than the resting amount, and during maximal exercise, it increases many times more, and that is about 1,000% change. Heart is a similar situation, not as dramatic as in the skeletal muscle, still quite high. Brain is an interesting organ where the blood supply is maintained steadily. Okay, exercise or no exercise, it's always going to be a continuous blood supply to the brain. Skin, again, receives a higher percentage during exercise. Kidneys, on the other hand, is where you would see less blood supply during exercise compared to the muscles or the heart or the skin, because these are the ones that are involved in the exercise. If one has to remove excess heat, the heart has to pump blood, skeletal muscle generates the force of contraction for movement. Another set of organs that receive less blood supplied during exercise is the gastrointestinal organs. Okay, liver, spleen are also in that category. All right, so we were looking at approximately 5 to 6 liters of blood during exercise. It almost doubles, and then during strenuous exercise, it almost triples. So that's the summary of how each organ varies in terms of its blood supply. Now the blood flow regulation is what we want to talk about. We will look at different regulatory mechanisms that are associated with blood flow. Autoregulation, regulation by the nervous system, regulation by the hormones. Okay, here we first talk about the local blood flow. Okay, local regulation is what you call as autoregulation. Autoregulation because the blood vessels near the tissue are asked to do certain things, basically vasodilation to increase blood supply. Okay, so ability of a tissue to maintain blood flow through local changes. If there is a stretch, if there are paracrine agents released, that could affect the local blood flow. Okay, so blood flow to the tissue is kept constant even if the blood pressure changes elsewhere. That is the goal to some extent. And then, if the blood pressure is really wacky, then it affects the tissues as well. So here is one example: increased tissue metabolism. Okay, increased chemical reactions within the tissue is when the tissue uses oxygen, so there is less oxygen available to tissues. Hypoxemia, that is less oxygen availability, and then that leads to release of vasodilators. These could be paracrine agents, okay, local agents, that is adenosine, lactic acid, histamine, ADP, and then increased levels of CO2, potassium ion, increased levels of hydrogen ion. All these could send a signal to the blood vessel and result in vasodilation, okay, increased tissue blood flow, local vasodilation, okay. Although this is possible in most of the tissues, there are some exceptions to this rule. Skin, for example, its blood supply is controlled by the temperature changes, whereas in the kidney, it depends on the amount of wastes or water to be removed, not necessarily coordinated by the local regulation. So now the tone, vascular tone, that is, whether it is constricted or dilated, is what you call as the tone. Muscle lining of the vessel and its tone is what we're talking about. Myogenic, that is the smooth muscle behavior, is the one that's causing vasodilation or vasoconstriction, is what you call as myogenic. Right? Now, who can change the smooth muscle action? Calcium ion. Okay, if there are fewer calcium ions, there is less contraction, and vice versa. The sympathetic tone, the vessels are supplied by sympathetic system, and anytime there is sympathetic activation, that could stimulate muscle contraction. So muscle contraction causes vasoconstriction. That's what you're looking at is, in this example, increased sympathetic activation, increased vasoconstriction, that would cause increased total peripheral resistance, and that results in venous return and cardiac output. We have seen this example before, and we are looking at this again in context to the myogenic regulation of blood flow. Metabolic theory, we already talked about how increased metabolism can lead to increased increased use of oxygen, therefore there is less oxygen available or less nutrients available, and that's when there is a release of vasodilators. Vasodilation improves circulation. Myogenic theory, again, we are coming back to the smooth muscle behavior, decreased arterial pressure, decreased wall tension. Okay, so if there is less blood pressure, there is less constriction. So the less pressure, less tension, there is more dilation of the vessel. So the pressure can also be able to change the vasodilation or vasoconstriction. All right, long-term local blood flow regulation is by adding blood vessels or removing blood vessels. So that is where you're talking about changing the degree of vascularity of tissues, size and number of vessels. Okay, anastomosis can develop. That means, blood vessels grow from one artery to another artery, or one artery to a vein, and so on. And basically, addition of capillaries and so on is typical when there is increased blood supply. All right, hormonal regulation is where a number of hormones are associated with the blood vessel function. That is, flow can be regulated through vasoconstriction. Which vessels cause vasoconstriction is where you're talking about epinephrine, norepinephrine, antidiuretic hormone, and angiotensin. This is angiotensin 2 to be exact. And the neural regulation is, as you already came across, vasoconstriction caused by sympathetic activation. Vasoconstriction, vasodilation. Activation of sympathetic system causes vasoconstriction, or the inactivation of sympathetic system would result in vasodilation, okay, in general. Now, talking about a vasomotor center that is involved in the regulation of the blood vessel constriction or dilation, vasoconstriction, vasodilation. So, vasomotor center, VMC, or cardiovascular center, is situated in the brain stem area, to be exact, in the reticular activating system. Reticular activating system spreads over the brainstem area, okay? So this is the one that has the vasoconstrictor and vasodilator centers, okay? Then there are other structures in the brain that would have their inputs to these two centers, hypothalamus, cerebral cortex, are some of those that influence the cardiovascular center. So here is one example. If activation of vasomotor center is the case, the blood pressure can change in seconds. Okay, so stress stimulating sympathetic activity causes increased total peripheral resistance, increased venous return, increased heart rate, increased contraction strength, increased blood pressure. And all right, while all of this is happening, you would also see that there is decreased parasympathetic activation simultaneously, so that the heart rate is not reduced but increased, and so on. Well, just a little bit about baroreceptors. Baroreceptors are sensory receptors found in the wall of the aorta and the carotid arteries. Okay, you call them as sinuses because these are the beginning parts of the vessels. Carotid sinus is like the very beginning of its branch. Aorta also very beginning of the aorta. Okay, that's where you see the concentration of those. As soon as the blood gets into the aorta, you should see the sensory receptors, and they then in turn would be activated. So baroreceptors are sensitive to a pressure anywhere between 60 to 180 millimeter mercury. So anytime there is higher pressure, that's when they are typically activated. Activation would cause inhibition of the vasoconstrictor. Okay, so higher pressure, for example, you want to lower the pressure. Okay, so that's the feedback effect. That's where you want to inactivate the vasoconstriction or trigger vasodilation. So vasoconstrictor is inhibited, and you would activate the vasodilator or activation of the vagal center. Those are the two ways by which you would bring about reduction in blood pressure. And another example of baroreceptor activity is when you change your position from the lying down position, supine position, to upright position. What happens is blood rushes into the legs, vessels in the legs, and the gravity keeps it down. So decreased volume of blood in the other parts of the body, decreased pressure, therefore, and now that would turn on baroreceptor activity. Okay, when there is drop in pressure, baroreceptors are activated. They would then increase vasomotor center and increase sympathetic activity, and therefore increase CPR and increase blood pressure. So the same thing is shown in here. Increased blood pressure is where you would increase baroreceptor firing, and you would turn off the cardiac inhibitor center, and turn on the cardiac inhibitor center, turn off cardiac accelerator center, and then also inhibit vasomotor center. Basically, what you really want to do is to reduce blood pressure because of the condition. There is increased blood pressure. So what you need to do is to turn off vasomotor center. Okay, therefore you would have vasodilation, and you would also activate cardiac inhibitor center, and that is the parasympathetic activation. Okay, you would turn off sympathetic activation. So decreased cardiac output, increased vasodilation. All right, all of these should result in a drop of blood pressure. So increased blood pressure should result in a lowering of blood pressure. On the other hand, if there is lower than normal blood pressure, there is decreased baroreceptor firing. So opposite events is what you expect. Exactly the opposite events compared to what you saw here. So that would increase cardiac output, increase vasoconstriction, blood pressure increases. So once you understand this half here, you can interpret this one easily. Okay, reversal of what you saw up there. All right, so it's a negative feedback mechanism. Similar to baroreceptors, we have another set of receptors called chemoreceptors. As the name suggests, they detect certain chemicals, levels of certain chemicals in the blood. Now, we are talking about oxygen levels, CO2 levels, and a hydrogen ion. So here, if oxygen level is low, or CO2 levels are high, and if you have too many hydrogen ions, that's when the pH would be lower, and those are the times chemoreceptors are activated. They are also located in the same location as baroreceptors. Chemoreceptors, in addition to being here, they're also present in the brainstem area. All right, so those are called central chemoreceptors, and the ones that you find in the aorta and the carotid artery are called peripheral chemoreceptors. Okay, so whenever there is a less than normal blood pressure, then there is less blood reaching the tissue, therefore there is a buildup of CO2. Okay, it's because you're not removing CO2 as readily. You may call that condition as ischemia, less oxygen supply, and the buildup of CO2 are all typical changes that you would expect with the decreased blood supply. What happens then? Because of the buildup of CO2, you would see the activation of chemoreceptors, which then turns on the vasomotor center, which then activates the sympathetic system, which in turn results in increased blood pressure. Okay, so not stimulated until pressure falls below 80 millimeter mercury. Got it? So that's how chemoreceptors function. Now, endocrine regulation of blood pressure is where you want to look at the list of hormones and their way of controlling blood pressure and blood flow. Okay, which hormones are we talking about? Kidneys. There are two key hormones. EPO or erythropoietin is the one that increases blood volume, and it also makes increased blood volume. What does that do to blood pressure? It increases blood pressure. And another hormone kidneys make is renin. Renin, by activating renin-angiotensin-aldosterone pathway, results in vasoconstriction. Adrenal gland, epinephrine, norepinephrine, and aldosterone are the three key hormones you want to talk about. Epinephrine and norepinephrine are the ones that cause vasoconstriction via the activation of the sympathetic system. Sympathetic system uses the release of epinephrine and norepinephrine, and that's how it causes vasoconstriction. Aldosterone through the renin-angiotensin-aldosterone system. Antidiuretic hormone ADH released by the hypothalamus is another vasoconstrictor. Okay, its name is vasopressin because of that reason. Okay, it also helps reabsorb water, that increases blood volume. Okay, now the heart would make atrial natriuretic peptide ANP, which is the only hormone here in the list that causes vasodilation, and it also gets rid of water in the form of urine, so it decreases blood volume. So it tries to correct high blood pressure situation. That is how atrial natriuretic peptide causes vasodilation and also remove excess water. All right, so that is the same thing that's summarized here. We are talking about decreased blood pressure and volume. Very quick result is through sympathetic activation. Okay? Certain changes in blood pressure can be corrected by sympathetic activation. Sympathetic activation, adrenal glands release epinephrine and norepinephrine. These hormones increase cardiac output, increase peripheral vasoconstriction, increase blood pressure. Okay, then a long-term effect is through the release of renin and erythropoietin. Okay, renin, angiotensin-aldosterone pathway. Then we are also talking about antidiuretic hormone. All right, all of that should increase blood volume. All right, response to loss of blood pressure. Here we talked about short-term versus long-term ways of regulating blood pressure. Here, in response to loss of blood pressure, decreased blood pressure and the volume, it could be due to shock, for example. What kind of endocrine mechanisms do we see? What kind of neural mechanisms do we see? These are repeats of what we have done. It's a summary, basically. You are looking at so when the blood pressure and volume are decreased, what kind of mechanisms are turned on is what is summarized here. Neural mechanism and endocrine mechanism. Endocrine mechanism is where this is decreased blood volume, decreased blood pressure, so we need to increase. So we need ADH, which reabsorbs water from the kidneys, it adds volume, and therefore blood pressure. So ADH is good, and angiotensin 2 is a very potent vasoconstrictor, and therefore that again increases pressure. Aldosterone reabsorbs sodium ion and indirectly reabsorbs water, and therefore it increases blood volume and blood pressure. EPO increases blood volume by increasing the production of red blood cells. Okay, so that is how you would correct the situation. What kind of neural mechanisms are turned on? Well, whenever there is a drop in blood pressure, baroreceptors or chemoreceptors or both are stimulated. Cardiovascular centers are stimulated via these receptors, and then general sympathetic activation. And all of this results in the increased cardiac output, and then increased peripheral constriction, increased blood pressure, and increased blood volume. So that is a typical situation when there is decreased blood pressure and blood volume. One other point that talks about here is decreased venous reserve because of the constriction, vasoconstriction. There is more blood being circulated than being pooled in the veins. All right, so this is where you summarize all of the regulatory mechanisms that exist: autoregulation, neural regulation, and endocrine regulation. Whether it's short-term, long-term, all of that is covered. Pretty much the same thing as we have talked about before. Autoregulation is local regulation, local reagents released. And the situation that would cause vasodilation is when there is low levels of oxygen, high levels of CO2, increased metabolic acids such as lactate, calcium ion, hydrogen ion, and nitric oxide are inflammatory agents, increased temperature. All of these lead to vasodilation, correct? Changes to blood flow detected by local receptors. There may be vasoconstrictors such as prostaglandins and endothelins. They are the ones that constrict the precapillary sphincters, decrease blood flow. All right, so both ways it can be turned on. And now we have just seen the neural and endocrine mechanisms that is summarized again here, okay? Good. With this, what we would do is to stop this video here, because we now have talked about the blood flow through the arteries and the factors that are associated with blood flow, such as resistance and blood pressure. And this is where we have gone in to talk about arterial blood pressure in detail and its regulation. Okay, so the next video will be focusing on blood flow through the capillaries, and then blood flow through the veins, and then so on. Okay, thank you.